Okay, hi everyone, welcome back to linear algebra. And quick recap, we learned last time how to multiply matrices row by column and and uh, and by the end of the class I've shown you a few examples and as to why I claim that matrices are actually functions, because when you multiply by a matrix, it can apply some kind of change. And I gave you the examples of a rotation matrix, which rotate vectors. And I also have shown you this matrix that subtracts each row from the row above it, and then I've shown you how does it look when you do it, apply it to an image. And the next thing we are going to study is a part, and just to make sure I've shown you addition and multiplication by a scalar, right? Yes, there it is. And so we are learning, right, Sammy? We are learning about the algebra of matrices and like with fields, we want to know what properties hold. Is the multiplication commutative? No, not in general. Shown, I'm pretty sure. Did I really? I'm not sure that I've given you an example for this. No, I think I didn't. Okay, so let's see a quick example now. The multiplication is not commutative. I think I said it by heart in general about the composition of functions, but I didn't show you this specifically for matrices. So this is a very important example. Multiply the matrix 1, 0, 0, 0 by 0, 1, 0, 0. Okay. And afterwards, I will reorder them and we'll see that we'll get a different result. So how do I apply the multiplication? How do I calculate the multiplication? I take the first row and multiply it by the first column. So it's 1 times 0 plus 1 times 0, which is obviously 0. Then I take the first row multiplied by the second column. 1 times 1 plus 0 times 0, that's 1. And then when I go to the second row, it's all zeros. So here I have 0, 0. Now, let's flip the order. And see what we get. Okay. So first row is 0, 1. We multiply it by 1, 0. What is the result of that? 0, because 0 times 1 plus 1 times 0. That's 0. And the second row is also 0, same as before. And the only interesting element is here. It's the first row times the second column, which is again 0. So you see that here A times B, here A times B is different than B times A. And another interesting fact about this example, and also we have two matrices other than the zero matrix, whose product is zero. So that's also something we are not used to in numbers. If you multiply two numbers different than zero, the result is always different than zero. Okay, I will state that claim. You can prove it as homework. And given a field F, then for any two numbers x, y in the field, it is true that x, y equals 0 if and only if x equals 0 or y equals 0. So that's in a field. This claim is false with matrix algebra. Okay.
So matrices aren't fields?
No, not a field. And it's good because I don't know if it's good, but maybe it was better if the word was simpler. But if it was a field, then it wouldn't be a specific field of interest, subject of interest. Matrices are linear functions. Linear functions are not number, they are functions. They behave differently, and their multiplication behaves like composition. Composition is not okay. Another thing, it's not a field because it's not commutative, right? By the second I've shown you that the operation is not commutative is already not a field. So this is redundant. But the reason that I stated specifically is that sometimes students get like, I'll really write it as an example. You get for some reason that AB minus AC equals 0. Okay? For some reason, assume that. Then first of all, you do that. What law, what rule did I use going from here to here? Distribution law. Is that allowed? I didn't even think of it when conjuring the example, but I will speak about it. The distribution law holds. Okay, so that move is correct. But then students say, then either A equals 0 or B equals C. Do you agree about that?
Not necessarily.
That's a false statement. Let me think of as to how to write it to you. Assume that is the following argument correct? The answer is no. There are other options. And again, for homework, find A, B, and C such that A is not the zero matrix and B is not C, and A, B equals to AC. Okay, so conjure up an example, a counterexample, and it has to do with this example, right? That's a good place to start, because then you can multiply two things different than 0 to become 0. So I urge you to try to do it yourself, but it's a common mistake in tests in linear algebra that you come to some multiplication, some product equals zero, and say, okay, so either things are zero. In fields, it is correct. In matrices, not at all. Yes.
So the distribution law does apply, but
Yeah, I will go over all of them. Okay, that's my point. I'm saying once we did algebra, once we have an operation, even in discrete mathematics, by the way, not always the lecturer choose to do it. I like it. You have seen the operation of union of two sets, right? Does it have a neutral element
union,
for union?
The
Is there an
empty set.
element? What?
the empty
The
set,
empty set is neutral. Does it have an inverse?
the empty set, or
No. Does any set have an inverse?
the complement.
No, because the union and of the set and the complement is the whole world. It's not the neutral element. And the answer is no. Union is not an invertible operation. Once you added things to the set, there is no way to take it back. Okay, so in algebra, in an algebra mindset, every operation immediately comes with all the rules and all the properties. Is union associative? The fact of the matter it's true.
Yeah.
Okay, and distribution requires two operations. So you can ask whether union and people
Intersection.
thank you. Whether union or intersection are distributed together. So maybe it won't be super important in discrete mathematics, but in algebra these are natural questions. So I go over them. Okay. So what were the 7 conditions, 7 properties of the field? The first was sgirut, making sure that when you do the operation between any of the 2 operations, between any 2 elements, it remains within the field. So matrices, you cannot multiply any 2 matrices you like. But if you stay at a square size, n by n, then you do have sgirut. The product of 2 n by n matrices is an n by n matrix. The next is the commutative law, which does not hold. Not hold for multiplication, does hold for addition. I will not talk about addition. With addition, everything works perfectly. Multiplication is the interesting part here. The associative rule, associativity, wait a second. Associativity, given A in the size in double F n by m, B a matrix of the size m by k, and C a matrix by the size k by r. Then A times B times C equals A times BC. Okay, that's the association rule, associativity, and that actually holds. Look at how different it is from commutative law. I'm not changing the order between the matrices, I'm just changing the order at which I apply the multiplication. And that's actually true, and that's really important. And luckily it holds. If that doesn't hold, not many algebraic mathematical structures are not associative. It sometimes happen, and then it's like a stick in the wheel of the bike. really stops you for doing a lot of things. Okay, so associativity holds. Okay, and I will not prove that, and I urge you. How do you write urge? Urge? Oh, you? Oh, right. I urge you, thank you, to try it at home, but it is hard. Okay, it's hard to understand. Some proofs use tricks, and then I wouldn't expect a student to be able to invent the trick themselves. But here it's straightforward. But the problem is all the indexes and sounds. It's one of the reasons that I'm skipping it, because in general, I teach you the linear one for mathematicians. However, their course is 4 hours of lectures and yours is 3. So something got to give, right? So these are the kind of things that I think are less important for you and I'm willing to skip. Because they are not actually linear algebra, but something a bit else. Okay. But I think you need to try to do it and see why is it complicated. Okay. You just need to prove that the element in the place ij of the left hand matrix it equals to the one to the right. And also why does it open that again? Are we lying? Yes. Okay. And also, all of the proofs that I'm skipping are in this link in Hebrew, but maybe it's enough for some of you guys. I'll remind you that I think I talked about this page on the first day. It wasn't the date on the first day. So this is here, I think. Yes. Hi. So this is specifically. So I'll give you a link to the whole page and specifically for that video if you wish to try to do it yourself. The link here. I remind you, and there is helpful material in Hebrew at following link. Okay. Great. Okay. So the associative rule works. Is there a unit element, meaning a matrix that when you multiply it by A, you get A?
The square matrix that is the same size as the columns that has ones across it and zeros in every other spot.
Are you guessing it or knowing it?
I think I saw it somewhere.
Okay. Okay, yeah. The answer is yes. And the unit matrix, and I'll define it, definition, and IN in double F n by n, which is defined in the following way. The element of the matrix in row I and column J is equal to, if I equals J, if I'm on the same row and same column, meaning I'm on the diagonal, the value is 1. If I is different than J, and the value is 0. Let's do a quick example. And let's take I3. That's a 3 by 3 unit matrix. So here, the number of row is 1, the number of column is 1, so that's 1. And also for the rest of the diagonal, okay, these are all 1s. And all other elements, say this one, it's the first row and third column. So I is different than J. What are the values here? 0. So this is the unit matrix. And claim proposition. I know proposition is more professional than claim. Proposition, given any matrix A of size M by N, then if I multiply IM by A, why specifically IM here?
Because it's the size of the rows, the amount of rows of A.
Yeah, in order for the product to be defined, the number of rows of A must equal to the number of columns of the matrix on the left-hand side. So that's M. And what is the result? What happens when you multiply by a unit? You get A. And also, you don't have a commutative law. So once you don't have commutativity, you have to mention everything twice. So also A times IN equals A. So it works on both sides. It's not just a unit from the left. It's a unit both from the left and the right. But it's a bit weird that it's different. And again, that's because matrices are like functions. So think of a function that takes people and outputs dogs. So if you wish to apply the identity function first, you need to apply the identity on people. If you wish to compose the identity function second, you have to take the identity on dogs. Okay, that's a little reminder from discrete mathematics and composition, which works. There you have the identity function IA, right? Did you see it in discrete mathematics?
Yeah.
You see in invertible functions. So they have the identity function, and it was the identity on the range or on the domain of the original function.
So with this, you mean that A is also a function, not just
All matrices
Yeah.
are function. That's what I'm claiming. I'm not actually using it in my arguments. I just urge you to think about it this way, and then the whole multiplication makes much more sense because it's not like a multiplication of numbers. It's not a field. It is like composition of functions, and that's why it looks this way. But the I don't know, the mathematical argument is that's the size. If A is not a square of a square size, then you have to multiply by different size matrices to the left and to the right, right? So that's the mathematical argument, but I'm trying to get to the more philosophical one. which is also mathematics, but fine. So I'll prove some of that. Proof. And why am I saying some? I'll just prove one of them. The other one is obviously quite symmetrical proof. So we'll prove that I am times A equals A. And this size first, we need to prove that the size of these sizes of these matrices is the same. Because if I wish to prove that one matrix, if I wish to prove discrete mathematics, the two sets are the same, how do we prove it are equal? How do we prove that one set is equal to another set?
That every element in the first set is in the second set and not any other element.
No, that's one inclusion.
That the XOR is the empty set.
No. You need to do double inclusion. You wish to show that every element of A is an element of B, and every element of B is an element of A. Okay? But these are not sets. Now we wish to prove two matrices are the same matrix. So how do we do that? First, we prove they are the same size, and then after I prove they are both the same size, what do we need to do?
We take the difference and check if it's zero.
No, but we need to make sure that every element is the same at some place, right? I will take a general ij, I column j, I row j column, and I'll make sure that the element in the row I column j on the left hand side is the same element as in row I and column j in the next element. So it's two steps. First, make sure the size is correct. Second, make sure the entries of the matrix are the same. Okay? So the size is pretty easy. Since I am is of size m by m, and A is of size m by n, then the product, what would it be?
Yeah.
M by n, and A is the same. Okay. And A is also there. Okay. So next now, and given I between 1 and m, and j between 1 and n, what is the element of I am A at the place ij? So first remember, we're taking the ith row of IM and we multiply it by the j column of A. And how do we multiply a column and a row? I do sigma on some kind of index from 1 to m over I am in the place I p times A in the place pj. And I'll try to remind you why is that true? Because when p goes, this is basically a for loop, right? It's a for loop when you do plus equal, right? So when P runs from 1 to M, I always remains the same, meaning that I stay on the I row, and I take the first element of the row, the second element, the third element, that's going through the row. And in this matrix, the column stays the same, and P runs over the row. So that's exactly this operation, which is the multiplication, and I multiply an element by an element. And then I sum them all up. That's the definition of multiplication of matrices. But here it's very nice. Why? What elements are in the row of the unit matrix? For example, this. Take any row. What are most elements of the row? 0. What is the only element in each row? Where is the only element in each row which is not 0? Not always the first. Yeah, the one on the diagonal, the one whose column location is exactly the row location, right? It's written here when I equals j, right? But I'm trying to get you to visualize it as well. In any case, the only element of the row Ri of IM, which is not 0, is located at the ith column, and thus get this equals I am at I times A at which place?
IJ.
IJ, exactly. And what does this element equal to?
1.
1.
And
So that's Aij. That's equal A at Ij. And that's exactly what we needed to prove. So I am at Ij is exactly A at Ij, which is what we wanted to prove. Therefore, I am A equals A, because they have the same elements. Any questions so far? So that's the kind of arguments I skipped before. I did that because it's easy enough. With associative rule, it's more complicated because it's a multiplication, 2 multiplications. So it's a sum of sums, which is a bit more confusing. But this that I don't usually prove, I chose to prove now. Okay, so we have a unit element, a matrix. Okay, what is the next question?
an inverse.
An inverse, exactly. I'll skip it just to say the distribution holds, and then I will get back to inverse. The next question is, do any non-zero matrix has an inverse matrix? These are all, if you don't remember, I just want to show you the properties of a field because we're going through all of them. I remember them, you probably less than me. So the first one is the product of two numbers is a number. and the sum of two numbers is a number. So with matrices, it's not really true, but with square matrices it's fine. The next one is the commutative law. It works with matrices addition. It does not work with matrix multiplication. So it's already not a field. But in any case, I wish to know which properties do hold. So the next one is the associative rule. It actually works. Then the unit elements, the neutral elements. So the zero matrix I didn't mention, but obviously is neutral for addition. If you add a matrix with all zeros, then it's neutral. And it's also have an inverse, the negative matrix, minus A. So that's, I didn't even mention, but it's easy. The unit element, that's a rather big thing, but there is actually a unit matrix. And so, like I said, negative matrices exist. And then we are left with an inverse, meaning a matrix when which multiplied by, you get the unit matrix. Here it's all only written A times the inverse. Because we don't have commutative law, and commutative rule, we will have to demand that both A times the inverse will be I and the inverse times A will be I. And lastly, the distribution law, which actually holds. So most of the things here holds, except commutativity and inverse. But these two are enough to make it not a field. The actual algebraic structure is called a ring. And you don't have to know it for this course, but
We saw it a bit, but not a lot for, I think it was
In a
the,
test, no?
yeah, in a test or something for discrete math. Or yeah, in
on a ring,
one, like you teach discrete, the last question, the question 5 for some test or some previous test was that this is a ring and this is the properties. And
oh really?
And then proofs and stuff.
Oh, interesting.
It was
Yes. Sounds like it, yeah. But there is also a choice course, not obligatory, in מבנים אלגבריים later on, and then
we have to
you
take
talk.
maybe-
No, מבנים אלגבריים? No.
no, that's
מבנה נתונים,
no,
אלגוריתמים.
no, I guess we can take it now if we want, or next or in summer maybe, because the prerequisites are only,
Yeah, but it doesn't
great.
exist in summer?
I'm not sure.
I don't think so. I was chosen to teach it next year, by the way. This year it was someone else. Next year they asked me to teach it again.
I'll wait for next year.
Yeah, yeah. After I finish teaching it.
No, you start next
Yeah,
year.
yeah, yeah. I'll wait for the year after that. It's Hebrew. It is a nice course, I think. I used to teach it when it was obligatory, and then they made it into a choice, and they also switched the lecture, and now they got me back again. I don't know if it means something, but that's just the history of the course.
It's a ring.
Yeah, it's a ring, yeah. No, it's yeah, but this is algebra. So for now, it's not that much important for us, even though the course is algebra, but we don't learn general algebra. We learn linear algebra. But still, the way of thinking is shows throughout the course. Okay, so before that big question, let me just claim, and again I will leave it for you as homework, proposition homework, given A of the size M by N and two matrices of the same size B and C of the size N times something, then A times B plus C equals AB plus AC. Distribution law. That's distribution.
Maybe you could suggest we do it as actual homework.
Yes. For the I don't know. To be honest, I don't mind about that at all. It's just for you, it will help you. And I wouldn't even I I wouldn't say that I think that all of you must do it. I think it's a good idea, but it's not the direction where I'm taking the course. So doesn't matter to me. Okay. So I'm not sure, by the way, this is even proven on the videos because the associative is of all the laws is the hardest. So I usually prove that in class and the rest I take as homework. But this is supposed to be quite easy if you know how to write the proof, which is the hard part. What else? Also, and I'll write it in real short, C times A times B. This does not fall within the regular rules of the field, properties of the field, because it involves two different multiplications, scalar multiplication, regular multiplication. But this actually equals to A times, first of all, C times AB, and also A times CB. There are some more rules, I'm not sure how, whatever, I'll write some of them. A plus B times A equals A plus BA. A times A plus B equals A plus AB. I hope I mention all these kind of rules. Let me just make sure. I think I wrote all of them here in order not to forget.
ABCS.
Oh, I didn't write the last one.
Small C and small A are
Scalars.
yeah.
Yeah. And lastly, oh, okay. All right. A, B, and C are members of the field. A and B are matrices. Okay, now I wrote it more formally. And the last rule I forgot was A times B times A equals A times BA. These are kind of things that even if I didn't tell you, you'll probably assume it's true. But what I'm telling you that every sentence here is a proof, is a claim that must be proved. But I'm not suggesting that we will do all of them because they are quite the same.
I think you need to split this into cases because you said
The multiplication, you're right. You're right.
I mean, you can state that.
That's why I try to avoid it, but
yeah.
and A and B are matrices. Okay. So
where the loss hold.
Yeah. Where the product is defined. You're right. Okay. So I think these are the main things to know about. And now, again, the main subject that we should talk about are the inverse matrices. Okay, that's the main thing. These are everything that works is fine. We want to know about what don't always work and know how can we tell if a matrix is invertible and how to calculate the inverse. That's the meaty part of the whole thing. And again, think about functions. The function that multiplies every number it gets by 0. It's the constant function 0. Agreed? Is that an invertible function?
No.
Obviously not. It's not one-to-one. And the reason I gave you this example is that you can think about the operation multiplying by 0, which is not invertible. You cannot cancel it, right? So if matrices are functions, some functions apply an invertible operation and some don't. And we need to know which which are which, right? So the zero matrix, if you multiply by the zero matrix, obviously it's invertible. It's not invertible. But what about, I don't know, the matrix where all the entries are one? Is that invertible or not? No zero, everything is one, right? So that's the question. And I told you all this by heart, and now I'm going to write another question that has to do with invertible matrices. Question. There are many ways to go about this question, and I'll chose one to write. Say 2x equals 6. What does x equals to?
Right?
Great, Thomas. But how did you know?
Because I made the inverse operation of multiplying x by 2.
We will multiply by the inverse of 2, right? And we will get x equals 3. Why do we get x equals 3? I'll show you it with the matrices with the greater explanation in a bit. But the main idea was, in order to divide by the coefficient, I must multiply by its inverse. Okay? We saw, hopefully we saw, let me just make sure that I'm not, I think, yes. I just give it as an example, not in general, but I hope you believe me that in general it works, that every linear system of equations can be is equivalent to a product of the coefficient matrix by the variables vector and equal to the constants vector. So we saw, I'll play with that. We saw that any linear system of equations is equivalent to ax times a times x, sorry, equals b. So if there exists an inverse matrix A minus 1, what will happen when we multiply by it? So we start with ax equals b. And we multiply by a minus 1. So we get the inverse of a times ax equals b. Okay. What is the next step we should take here?
I mean, if it's the inverse, it should just give us the vector x equals b.
But why? What is the very next step?
Distribution.
Associative.
I mean,
Associative.
is it associative?
We said, yeah, we said that matrix multiplication is associative, right? We
Okay.
went through all the rules, and the only ones that did not work were inverse and commutative. The rest works. So it's, first of all, we use associative rule. So we get this. Oh, sorry. I forgot to multiply on the right. So you get this. what would be A minus 1 times A?
I
Yeah, because that's the idea of an inverse. Once you multiply it, you get the unit. The unit here is the identity matrix, the unit matrix. And so I x equals A minus 1b. And what's I times x?
is it defined? necessarily?
Yes, yes,
I mean, then it should be X.
x, yes. And that's the very same notion as here. We multiply by half. Half times 2 is 1. You don't write the 1 because 1 times anything is anything, right? So it's the same thing, and I told you I will write it with greater detail now, right? And we're seeing almost everything. There is something else interesting about it that I will show you in a second. But the idea here is that in order to solve a whole system, so in order to solve the whole system, it is enough to so-called divide by the coefficients matrix. So what I'm saying is that the system, whole system of equations is basically like one equation. I just need to divide by the coefficient of the variable. But here it's a matrix. Okay, so if it's possible, it's great. Okay. It's not as great, to be honest, because you will see that in order to find the inverse, you actually need to solve the system first. So it's a bit silly, but there are uses for it. First of all, obviously in the theory, which are very important, but there are also uses in the real world, so-called. Sometimes you get the same coefficient matrix, but different constants. Like think of the coefficients as the rules of physics, and the constant as the data about the first speed, first location. So sometimes you need to solve the same system with different constants. So it's better to one time find the inverse and each time multiply by it. Technically, in this course you will not solve a system of equations this way most of the time. Okay, but still it's a cool realization that once you have an inverse, then a whole system of equation is just equivalent to one equation, and you just need to divide by the coefficient. Okay.
And just as a reminder, the variables vector is always a column vector,
Yes. Yeah.
and the v is also always a column
Yeah.
vector.
Yeah.
Okay.
Yeah. That's the way the multiplication is defined even. That's also the way I shown you why, because the coefficient must meet the variable.
Yeah, and I
So
just
it
asked.
must be this way in order for it to work.
Yeah, I just asked because when you're multiplying by the inverse, it doesn't matter what inverse you use, the previous inverse or the.
No, oh, so that's okay. So I'll answer you with a spoiler. There aren't two. There is only one inverse. Just like in discrete mathematics, when a function was invertible, it has only one inverse, and it was the same to the right and to the left. The same holds for matrices. We'll see it in a bit. But for now, in these short lines, in what order did I use that the product of A and its inverse are I? Only in one order. First the inverse, then A, right? I didn't use the fact that A times A minus 1 also equals I. So it looks as though it's enough that the inverse will be from the left, but it's false, and I'll show you why.
How can there be only one inverse if there can be
It's the
two-
same matrix.
No,
You're
yeah. I mean, just there's a one inverse, but there are two identities, both possible identities.
The answer is that A must be a square matrix.
Okay.
These are the only invertible matrices. Okay. Okay. You got it? Okay. We showed here that if AX equals to B, then X must equal to A inverse times B. But is there necessarily necessarily a solution to the system? Because in the proof here, I start with the equation, but maybe this equation is always false for every x. Okay, can someone guess if we can be sure that there is a solution here? When A has an inverse, that's our assumption. We assume that A has an inverse. And here we've shown that if there is a solution to AX equals B, it must be this. But does that it has to be a solution? Maybe there is no solution. How can we make sure this is a solution?
To the system.
Yes.
Like calculating,
What?
calculating,
What do you mean?
like calculating the inverse matrix.
No, but that would be specific. I want the general theorem. I wonder if always when A is invertible, then the system will have a unique solution. I've shown that there is no more than one, because X must equal this expression. But maybe this expression is not a solution. So how can we make sure? We plug it into the equation. Okay. In order to prove that X equals A minus 1 B is indeed a solution for AX equals B, we simply plug it in. And we get A times A minus 1 B. And we ask whether it's actually is equal to B. If it is a solution, right? And is that true?
I mean, I guess by definition, yes.
Not by definition. You need to prove it. Why is that true? So what will be the next step here?
Associativity.
Associativity. So it's A times A minus 1 B. And what is A minus 1? A inverse?
I.
It's I B, which is B. And here, look, we used A inverse the other way around that we used it here. So actually to know that when a matrix is invertible, you have a unique solution to the system of equations, you actually need both sides. You use A times the inverse and the inverse times A in the proof. Okay. So conclusion of what I've just written, if there exists a matrix, an inverse matrix, A minus one, such that A minus one equals I, and A inverse times A equals I, then the system AX equals B has a unique solution. So that's one way to look at invertible matrices. It's not the only one, but that's the one we started with, linear system of equations. So here, how invertible matrix help us in this question, but it will help us a lot in other questions as well.
I was going to ask if this proves the general case.
Yes, yes. The proof is above.
No, yeah, I mean,
I've shown that if there is a proof, if there is a solution, excuse me, it must be this. And I've shown that this is indeed a solution.
I meant the general case has matrices, not the systems of equations. Because
No, but general case of what?
like every matrix can be interpreted as a system of equations, so we can say.
But still, the claim here is about system of equations.
Okay,
I'm saying if the matrix is invertible, then the system of equations has a unique solution. So I didn't claim anything not about it, but it's also if the matrix is square, it's also the other way around, meaning that if the system has a unique solution, then the matrix is invertible. But I'm not mentioning it now.
okay.
And I wish to give you an example. We didn't learn how to invert matrices yet, but we will use matrixcalc.org here. Not matrix clock, matrix calc. Okay. Hopefully it's the right address. So let's take some system of equations. Let's do it 3 by 3. So x plus y plus z equals 1, x minus 2z equals 2, y minus z equals 3. The matrix form is the coefficient matrix is 1, 1, 1, 1, 1, 0, minus 2, 0, 1, minus 1. The variable matrix vector, whatever, it's the column x, y, z. And the constant vector is 1, 2, 3. Okay, so all right, this is the A I've been talking about. This is the vector x. This is the constant vector b. Okay, so by the above proof, the solution ought to be x equals a minus 1 times b. If the matrix is invertible, I really hope it is. But like I said, we did learn how to make sure if the matrix is invertible and how to calculate the inverse. So we'll use the computer for now. Then we'll take a break, and when we get back, I will show you how to make sure it's invertible. So matrixcalc.org again. The matrix was 1, 1, 1, 1, 0, minus 2, 0, 1, minus 1. Inverse. Yay, it's invertible. Pretty horrible. I should have thought about it, but whatever. You can essentially multiply it by 4. Nah, I won't change it, whatever. So the inverse is actually, I'll copy that. When I can write it in an integer fashion in the following way. A minus 1, the inverse is a quarter of, then just make sure not to make a mistake. 2, 2, minus 2, 1, minus 1, 3, 1, minus 1, minus 1. And therefore, the solution, so x, y, z would be this times the constant vector 1, 2, 3, which is a quarter times. So 2 plus 4, no, 2, yeah, 2 plus 4 is 6. Minus 6, the first element is 0. Interesting. Then 1 minus 2, it's minus 1 plus 9, that's 8. And here 1 minus 2, that's minus 1, minus 3, it's minus 4. Altogether, it's a nice result. It's 0, 2, minus 1. So theoretically, this is supposed to be the solution to the linear system of equations. The x must equal 0, the y is 2, and the z is minus 1. Let's look at it geometrically. So every equation here is a plane on the 3D vector space, and their intersection is ought to be at 0 to minus 1. Let's make sure it happens. Okay, so the first one was x plus y plus z equals 0, x equals 1, sorry. Color to mustard. Then x minus 2z equals 2. Eggplant. And lastly, it was y minus z equals 3. Broccoli. Okay, so there is indeed an intersection, a singular intersection of these 3 lines. And I already see the 2 here, but let's make sure. 0, 2, minus 1. Okay. Okay, you see that actually we solved the geometrical problem of a complicated one, right? But still, we solved a geometrical problem with only algebraic tools. And again, you didn't see how did we find the inverse, right? And in order to find the inverse, we need to do Gauss elimination on the matrix, which seems a bit redundant, but that's the case. Like I've told you before. So indeed, this is that. Any questions up until now? So I want to say anything else about that. I'll just write the definition. So after all that, definition. Matrix A is called invertible if there exists a matrix, if there exists matrices B and C such that A, B is I and CA is I. And note, B must equal C, since, and it's a neat trick. I guess you've seen it in discrete mathematics as well, but in any case, I will show you it. What is A times, sorry, what is C times AB? So on the one hand, it is C times I, which is C. Agreed? But on the other hand, due to the association rule, it's CA times B. But what is CA? So it's IB, so it's B. So B equals C. So there is only one inverse matrix, not two, like you rightfully thought, one to the left and one to the right. It has to be the same matrix, which we denote by A minus 1. If it's invertible, obviously, it could be not invertible, but if it's invertible, then there must be a unique inverse matrix, which is called, which we mark by the inverse A minus 1.
You can basically state that A has to be squared only by this fact.
No, no. Well, everything I wrote here would work for rectangular matrices just as well. It's not an easy proof to show that it must be a square matrix.
I mean, for this to work, C has to be equal to B, and for the multiplication to be defined, it has
They
to
could
work.
no, they could be. B and C must be the same size, but you can if A is M on N, then B and C are N on M, and the multiplication is defined on both sides. It's not by size, it's something else. Okay, let's take a break until 2:30.
They go to time.
I mean, there's a connection between invertibility and I mean, the girl I'm going out with is
Yeah.
Okay, and we're back. So, and the next big questions are, how do we know if a matrix is invertible? And if so, what is the inverse matrix? So these are the two things we wish to learn about. And how to say it? It surprisingly, the technical algorithm of Gauss elimination will save us here as well. So what I was struggling with is to explain to you why is it so surprising, because Gauss elimination was thought of up until now as the way to solve a system of equations. We sum up the equation in order to cancel the coefficient and whatnot. But here we use the same algorithm altogether in order to find an inverse matrix which has little to do with a linear system of equations. I did show you how does it also help to solve a system of equation, but like I said, matrices are functions, and we wish to find the inverse function. So how does it work? First, we notice that if F from set of matrices to the set of matrices is a function that applies one of the elimination operations, then if I apply the operation to the identity matrix and then multiply by A, what do you think will happen? I apply the elimination operation, and there's an S here, it's a 1 elimination operation. I apply the elimination operation to the identity matrix, to the unit matrix, and then I multiply by A. What do you think will happen?
The result won't be A.
It obviously won't be A, but what will it be?
A plus the difference, like.
Let me give you an example before I finish the sentence. Example. Choose the size will be 3 by 3. choose any operation, any elimination operation.
Sum row 1 to row 2.
Okay, so F would be R1 plus R2. Okay. Let's apply it, and M, like I said, would be 3. So let's apply it to the identity matrix. What is F of I3? So I'll take the original identity matrix, 1, 0, 0, 0, 1, 0, 0, 0, 1, but I apply to it and the operation that Thomas chose, just for an example, add row 2 to row 1. So what will be the matrix after the addition?
1 1 0 0.
1 1 0. Okay, so that's that. Sorry. So I'm applying the elimination operation to the identity matrix, and I get this matrix. Okay, now my question is, what do you suppose would happen if I multiply that new matrix which I got in an oddly way, right? I do the operation on the identity matrix and now I'm multiplying. What will happen when I multiply it by A? So I'll continue with the example, and I take this matrix and I multiply it at the matrix. I need 3 rows, and I don't know, 2 columns it's allowed. A, B, C, D, E, F. So what do I get? So it's 1 times A plus C, A plus C, C plus D, C, D, E, F. So what did this matrix did to the other matrix?
Because the second to the first row.
It did the very same operation. So now, what do you think should I write here? F of I times A equals to
F of A.
F of A, exactly. Exactly. Okay, that means that if you wish to do any operation, elimination operation of the 3 we learned on a matrix, you can simply multiply by the correct matrix, which is doing the operation on the identity. It's not a proof, and again, I will leave it for you as homework to prove that it's always true. But for me, it's more important that you understand the concept that instead of doing operation, we can just multiply by matrices. In computer science way of thinking, it's much easier to do the operation than multiply the 2 matrices, because multiplication is it's how many operations does the multiplication of 2 n by n matrices take?
2n by n, n to the 4th.
N to the 3. Why? Because there are n squared entries, and each entry is row by column, which says take n operations. So it's n times n squared, it's n cubed. So it's a lot. It's much more than simply doing the operation, which is just n operations. But we need it not for actual calculation, but for the theory. Okay, and you will see so in, I don't know, a few minutes, how do I use this fact in order to find the inverse matrix? Okay. So proof or homework. Okay. I did that trick a lot today, but like I said, this is one of the subjects that I had. I chose to do quickly than I do with the mathematicians. Okay. So another interesting thing now, since each Gauss elimination operation is invertible as a function, right? If I add a row, I can subtract a row. If I multiply by a constant, I can divide by the constant, right? So since the Gauss elimination is invertible, so are these operation matrices, and I'll show you why. If what is f of f minus 1 of I, this is obviously I, right? If I do an operation and cancel it, I get back to the original matrix. But f of, in order to apply those operations, I multiply by f of I, or one operation. In order to apply the operation f, I need to multiply by the matrix f of I because of what I said earlier. So we see that the multiplication of these two matrices is I. And similarly, f inverse of I times f of I, meaning do both operations on the identity matrix, is also I. This means these matrices are the inverse of each other. And why does that help me? Proposition. Assume A and B are invertible, and the product AB is defined, their sizes match, then the product AB is invertible. The product of two invertible matrices is invertible. And what is the inverse? That in itself is rather interesting. What is the inverse of A times B?
The inverse of A times the inverse of B.
Good, wrong answer. Nice, wrong guess. Think about it like this. I think I gave you this example. I will do it again. You have two operations. One is getting your baby to open his mouth. The other one is inserting a spoon in his mouth, right? So if I made the baby open his mouth and then insert the spoon, how can I cancel what I did?
First the inverse of B and then the inverse of B.
First take out the spoon and then make him close his mouth. Exactly. It's the other way around. It's not intuitive because we're not used to non-commutative multiplication. But when the operation is non-commutative, that's the way the inverse works. So it's B minus 1 times A minus 1. Okay? And proof. That's a rather easy proof. Why? Because in order to prove that the inverse, in order to prove that the inverse of AB is B inverse A inverse, what do we need to do?
Multiply them together.
To multiply them, exactly. I like this proof because when you look at it, you're not sure what can you do, because we are used to start with an equation and then do stuff. But what we actually need to do here is actually read out loud what does the proposition claim, and then it becomes obvious. If I want to say that one matrix is the inverse of another, I need to multiply them. And what do we wish to see?
That they divide.
Yeah, that we get the identity matrix. And the multiplication is rather easy. AB times B minus 1, A minus 1. Due to the associative rule, we can use the parentheses wherever. So it's A, B minus 1, B, oh, sorry. B minus 1, A. Yes. Yeah, thank you. I didn't get any specific song to my head. That's it, okay. So it's B times B minus 1 is I. So you get A minus 1, which is I. And also B minus 1, A minus 1, AB also is I. And you see here why the order must be reversed, because you wish B would see its inverse. Think, Thomas, if you multiply AB by A inverse B inverse, then B would see A inverse and nothing would happen. And because the multiplication is not commutative, you would have get stuck with it. Okay? So we've seen this nice principle, but we've also proven, that's what I need currently, that the product of two invertible matrices is also invertible.
In discrete math, it works exactly the same, right? That it
Yes, that's because it's function.
Yeah.
It's function. Then, so sometimes a student might think to himself, so why don't I use just all the facts that I proved in discrete math? And the answer is maybe some of them you can skip, but some of them you need in order to prove that a matrix is actually a function. You need some of the things, mostly the associative rule. It's really important. I'm not sure if that may have been a result of discrete math, but the fact that A is a function and that any matrix is a function requires us some of the things I claim here.
I mean, yeah, also for that you have to do all the work to prove that a matrix is a function.
Yeah, that's
of
what I'm
a
saying.
field, yeah.
Yeah, that's what I'm saying. To prove that it's a function needs at least the associative rule. Why is that so important? Because the associative rule, its proof in linear algebra is horrible, and in discrete mathematics, it's 2 seconds. And you say, how could it be if they are equivalent? And the answer is that in order to prove that matrices are actually functions, you need to prove first the associative rule. So, but here I'm not sure. This could be, I never thought about this specific thing, because the proof is just as simple as in discrete mathematics. So yeah. Okay. So theorem, which is a conclusion of what we did. Given a matrix A, denote its canonical form, reduced echelon form.
It's with an
It's within it, yeah, I guess,
Okay.
right? Yeah, reduced echelon form. And in Hebrew, we call it Tatsua Kanonit, but it's more than Hebrew because canonical form is an English term that is used quite a lot in mathematics. So it's weird that they didn't use it here, but I will say canonical form. So denote its canonical form as CF of A, canonical form of A. Okay, so you have a matrix. You can do Gauss elimination, meaning do operation after operation. Eventually, you get to the canonical form. What we proved that instead of actually doing the operation, you can multiply by some invertible matrix. And the whole process will be the product of many invertible matrices. But what is the product of invertible matrices? It's also an invertible matrix, right?
So is it that the product of all the matrices that you do to
Yeah,
put it to echelon?
exactly.
That's the inverse
Yes,
matrix.
and you use the associative law to say that instead of multiplying one by the other, you can first multiply them all and eventually and finally multiply it by A. Okay? And you will see it's really cool you'll see in 2 seconds how powerful is this little notice that we did. So the theorem, given a matrix, denotes its canonical form. Then there exists an invertible matrix P such such that P of A is the canonical form of A. Okay, and yes, I'll write as explanation. In order to get to the canonical form, we applied E1 some operation to A, and then, right? And then we applied E2, and then I'm never sure how to write it with the parenthesis, but let's just do like this. And 3 dots EK. Okay, you understand what I'm saying? I do first operation I apply to A is equivalent to multiplication by the E1 matrix, and then I multiply by the E2 matrix, and finally I multiply by the EK matrix. By the associative rule, I can say that it is EK times E1, and that times A. And like Sammy said, the product of all the operations is the matrix I called P, which is invertible as a product of invertible matrices. Okay, agreed so far? So far, it's not even as cool as it should be. But it is cool that the entire process of Gauss elimination is basically a multiplication by one matrix P. Can you guess what is the matrix P? That's the really surprising part, because you saw, if you did homework, that you can do the elimination in many different ways, right? You don't have to go exactly the same way. So one would expect maybe that the matrix P could be a lot of matrices, right? If one did Gauss elimination in one way, we'll get one elimination matrix, and someone else will get another thing. But apparently, at least when A is invertible. Now, if the canonical form of A is the identity matrix,
P is equal to A.
No, in percent.
then PA equals I, right? Because PA is the canonical form. You see where I'm going with that?
Hopefully,
So what is P?
the inverse of A.
Yeah, multiply by the inverse of P, because P is invertible. I know nothing of A now, but P is invertible. So I can multiply by the inverse of P, and what will I get?
A
A equals to,
I times the inverse of P.
which is,
A.
no,
The inverse of P is A.
yes, yes,
No? Yeah.
right? So instead of proving that P is the inverse of A, we actually prove that A is the inverse of P. But that's a symmetrical definition, right? So P is the inverse of A. The product is I on both sides. So so we found a way to make sure that A is invertible. But more than that, even more than that, if we put A and I and me, sorry, if we put A and I, the identity matrix, next to each other, and apply Gauss elimination.
Sounds like a car died.
Elimination on both. The same operations on both. That is equivalent to multiply both by the elimination matrix P. So if A was next to I, and we did the same elimination, on the left-hand side, we'll get PA, and on the right-hand side, what will we get? We'll get P times I. Agreed?
Puppy.
No, not the time.
Yes.
Okay, puppy.
Right? If I do the elimination, I just convince you, hopefully, that doing elimination process is like multiplying by a matrix. So if I do the same process on both matrices, I multiply by the same elimination matrix. They're both, right? What is PA?
I.
It's I. If it's I, if it's not I, it's not invertible, to be honest, but assume it's I. And what do we get to the right?
P.
P. And what is P?
The inverse of A.
Yes. So this is the way to find the inverse matrix. You simply start by writing A to the left and the identity matrix to the right. You simply do Gauss elimination, and by some kind of dark magic, at the end, on the left-hand side, you get the identity matrix, and on the right-hand side, you get the inverse of A. Before start the class, right? Now you can enjoy linear algebra actually.
You just missed the puppy.
It's still here. Happy, not puppy. Okay. But this was the stuff you should be excited about, I think. Sammy, do you appreciate it?
I appreciate both this and puppy.
Yeah, okay.
Yes, okay.
But Pappy more, because I understand it, yeah.
Wait, but I understand all of this. I don't understand what you were trying to denote with a pipe.
Side by side.
Okay.
I just write them side by side.
Sure.
Okay. And we'll see an example now, right? Example. It's the easiest way to do the same operation on both, just writing them as if it was a large matrix. So matrix to the ampersand. No, it's not like that. Matrix to the ampersand. Wasn't enough. Inserts column. Okay, let's do 2 by 2. 1, 2, 3, 4. And
zero.
so this is the matrix I wish to invert. 1, 2, 3, 4. So what did I tell you to do? Next to that matrix, put the identity matrix, which is 1, 0, 0, 1. Agreed? Now I'm doing Gauss's elimination, naming R2 minus 3R1 for first. And then I get 0, 4 minus 6, right? It's minus 2. This minus 3, it's minus 3. Okay. Then divide the second row with minus 2, or minus 2, R2, to obtain 1, 3 over 2, minus 1 over 2. Lastly, what is the last operation here?
1 minus 2 or 2.
1 minus 2 times the second row. And we get to the left, the identity matrix, and to the right, 1 minus 3 is minus 2, and 0 minus minus 1 is 1. So here you see an example of exactly happy, right? I started with the A and the identity matrix. All of the operations put together are equivalent to multiplying by P. P is the multiplication of 3 matrices, the one that does this operation to the right, then this to its left, and this, and then this to the most left. So altogether they are P. And when I multiply A by P, I get the identity matrix. That's the canonical form, the reduced echelon form here. And to the right, I get P times I, which is just P. But I've proven to you above that this specific P must be the inverse of A. So P is good. And the inverse of A is this matrix.
I mean, it feels like a wild concept, honestly.
What do you mean wild?
Oh, you
Like-
don't work out the inverse matrix the other way?
No, I mean, it feels like very strange that you can perform Gauss elimination on a matrix that isn't a system of equations and it helps for anything.
Yeah, I agree that it's weird, but it's a little bit because of the order we learn stuff. Because think about it the other way around. This is the way to invert a matrix, and they're saying in order to solve an equational system, invert the coefficients. That makes sense.
Yeah, no,
right?
no,
it's
no,
just
no.
semantics, right?
No, not the
But I
semantic part.
agree. But I agree that it's a very technical process, and it's fine. It's the
Yeah,
inverse.
it just feels weird to think of it as a collection of vectors that you can sum and divide between them, and it just turns out that you can use them for anything.
I agree, but basically it's the idea is to break invertible matrices into small invertible operations, small steps. That's the idea. So it both works for solving a system of equations, but it also works here. But that's the theory. The practice of it, it's that we do the elimination and we find the inverse, I wrote P and but I agree with you, Thomas. And that's what I said as well. It's surprising. It's surprising that it's even more than that Gauss elimination will remain a thing throughout every question, every technical question in linear algebra 1 and 2, you do Gauss elimination. It doesn't matter the subject. It's always Gauss elimination. That's surprising, but it also with determinants and eigenvalues and whatnot, it's always Gauss elimination. It's surprising, but it's the truth. Any other questions? Sam, yeah.
Do we learn the other way of finding the inverse matrix in this course or not?
The only other way that I know of is using the determinant,
Do we do that?
but it's usually
It's
harder.
No, exactly. Do we do it?
Yeah. And no, because we don't learn determinant in linear 1.
Oh, we don't?
No,
Oh, no, you-
determinant is linear 2.
Okay. All right. Thanks, Todd.
An interactive.
Okay. So how can we make sure, how can we verify, not make sure, that this is indeed the inverse of that matrix?
We multiply them.
And what do you expect to get when you multiply them?
Identity.
Exactly, and let's do it. At least at one side on both.
Where is Gleb when you need him for him to say obviously it's the inverse? Like
Yes, obviously. It just needs to say obviously because the rest of the sentence
It's
is
obvious.
Exactly. Sometimes just looks at me and I understand that it's obvious. Okay, so 1 times -2 is -2 plus 3. Who would believe that OMG 1? 1 times 1 plus 2 times -half is 0. And 3 times -2 is -6. Plus 6, 0. 3 times 1 is 3. -2, 1. Okay, we actually found an inverse matrix, and the nice thing is that it works in any size of a matrix. Any questions so far? Fact, which I still to this moment did not decide if I wish to prove or not. An invertible matrix must be square, i.e. in the set of matrices with the same number of rows and columns n times n. Okay. Another fact, given a square matrix A and assuming that AB equals I or BA equals I, then B must be the inverse of A. Okay, so first of all, you can use both these things, whether I'll prove it or not. I tend not to in order to finish the material of the course. So the first some lectures simply defined the invertible just for square matrices. But I actually tell you it's more than that. Only square matrices could be invertible. And the second fact I do wish to talk about for a few minutes, it seems like I didn't say anything because the definition of the inverse matrix is when you multiply, you get I. But the thing is that I give you as an assumption only one side I tell you A times B is I. Only one side. Does that mean that B must be the inverse of A? In general, the answer is not. It's true for square matrices. And look at the following example to see what I mean. Example, multiply 1, 2, 3, 5, 6, and 1, 2, 3. Okay. And this matrix will be 1, 0, 0, 1, 0, 0. And this matrix will be 0, 1, 1, 0, 1, 0. And the product you can do yourself. I just tell you the answer is 1, 0, 0, 1, or in its other name, I2. Agreed?
Mhm.
Let's multiply them and invert the order. So first of all, Thomas, you will see now that the product is defined. You thought it might not be defined. It is defined. But what do we get?
0.
Not exactly. Not exactly. It's a 3 by 3 matrix, first of all. But it could be I theoretically, practically it's not. It is 1, 0, 0, 0, 1, 0, and lastly 0, 0, 0, which is not I. So that means that these matrices are invertible, not invertible. Because if they were invertible, it's supposed to be the same matrix that invert you in both ways. But here I saw that on one side you get I, and on the other side you don't get I. So this has to do with both these claims. I'm saying it couldn't be invertible because it's not a square matrix, and the fact that one side was I does not make the other side also I. In fact, it's definitely not I, because if the other product was also I, that means that this matrix is invertible, and like I said, that's impossible. We might prove it somewhere down the line.
I mean, I understand why you make a distinction between this and what and like an actually invertible matrix, but does this not hold any interesting properties?
It does, and I don't know if you saw it in this tree, but sometimes you have the definition invertible from the left or invertible from the right. In linear algebra, it's not that important, but in general algebra, yes, it's important. We use it sometimes, one-sided invertibility. Okay. Quick definition. I never know when to do because it's not connected to most things, but we sometimes do it. Definition and the transposition of a matrix given a matrix A of size m by n, we define its transpose matrix A T to be a matrix of size. I don't know if a capital T or small t. I usually write small t. And to be a matrix of the size n by m by A transpose in the place ij is simply the original A at the place ji. Let's look at let's see an example and see what it looks like. It's rather easy and sometimes important, useful. I won't say important. Transposition. Okay. Example. Say A is 1, 2, 3, 4, 5, 6. So A transposition of A would be a matrix with 3 rows and 2 columns, first of all. And then you say 1 is at first row, first column, 1, 1 stays the same. Here, who is at the first row and second column? I take the second row and first column, that's 4. And basically, I just write the rows as column. Simply, we write the original rows of the matrix in columns, or vice versa. And the original columns of the matrix in rows. So it's kind of, I don't know, like putting it on the side. A lot of time it helps us change from row to columns or from columns to row, and we have some way to answer questions about the column of the matrix. So we do the transpose, and now the rows on columns, and now we can speak about the original rows, which are the columns of the new matrix. I don't have a lot to say about it currently, but it's sometimes helpful using during proof. Sorry.
Is there an easy way to represent this as a matrix operation?
The multiplication, definitely no, definitely not. Let me think about it. I wanted to say definitely not, but I'm not sure.
Well, you can prove it.
No, I wonder
Eight
even if
times
the
P
size
equals
could
T, and figure out.
happen. I think the answer is no, because if I multiply by some matrix, the size of the no, definitely one of the sizes will remain the same, and in either the rows or the columns, by the definition of multiplication. And in the transpose, both the size, the number of rows and the number of columns is changed. So definitely, I cannot replace the transpose by a multiplication by a matrix. Maybe multiplication by 2 matrices. I haven't given that much thought, but this seems like it would work. But simple answer is we don't do it. Okay. And the reason why it's not that important is that we use Gauss elimination, as you saw, to prove many things. And transpose is used to prove not a lot of things, and usually, like I said, just switching rows to columns. And for that, I don't need to prove that it's a multiplication by a matrix. Okay, but it will be used sometimes again. So going by the chapters of the course, we finished the first 3 and we're about to start the 4th, vector spaces. So we had fields and the complex numbers, we had linear system of equations, which will be on the test. We had the algebra of matrices and product of matrices. When I skipped a lot of the proofs, but I shown the main claims here. And now we're about to start speaking about vector spaces. And the main idea of the course is learning about linear transformation or linear functions, which are actually, like I said, matrices, but I need to define it and prove that. And that's it, because the last chapter is determinant, which we don't have in linear one, and it's good. That subject is out the door, and we have the remaining two, vector spaces and linear transformation. Okay. So we don't have a lot of time, but we have enough time for some kind of introduction. So the subject is vector spaces and introduction. What is a vector?
Matrix that has either one column or one row.
That's not a general definition. Forget what we learned so far. Done.
It's an element in a vector space.
Done. No. But what, seriously, if you ask a layman person who finished 5 יחידות, what would you say a vector is?
Direction.
And
Just
magnitude-
direction?
a magnitude and a direction.
Magnitude and direction. The geometrical slash physical, is it right to say physics slash physical
Yeah.
way of thought is a magnitude and direction. גודל וכיוון in Hebrew. What is the algebraic way? Which is more relevant to us, right? The algebraic way. A point in space. And I'll show you this.
Isn't that still geometric though?
I'll show you this. Sammy, give me an example for a vector.
2, 1.
Exactly. What did you do? You gave me an algebraic answer, right? You gave me a bunch of numbers. You didn't give me a direction. You didn't give me a magnitude. You just you see why I'm saying it's the algebraic one? So I'll use that example. I just wish to move down the page. So for instance, look at the vector which Sammy gave, 1, 2, that's the algebraic representation. And look at the vector, Thomas, give me another one.
5, 3.
5, 3, okay? Everyone, what is the addition of B and W? What is the sum of these two vectors? 6, 5. Agreed by everyone? How did you calculate it? Geometrically, physically, or algebraically?
I just turned everything into matrices and it made sense.
It is nor the right answer, neither the right answer nor helpful. So is this algebraic or geometric?
Algebraic.
It's just algebraic. What both? Who are you
When you
kidding?
take the vector,
Did you
and then you
graph
take
it and
W,
then-
It's
and then
I
you take out
asked
the
how you solve it, not
That
if
is how I
someone.
solved it.
Oh, you did the direction, you found out the angles, you summed up the angles. Liar. Pants on fire. Okay, so you obviously did it algebraically, but you are correct, and that's kind of my point, that there is also a geometric interpretation. And there is a geometric interpretation for the basic vectors. Later in mathematical life, I'm not sure how we use it, but in this course a bit, you see vectors that has no geometric interpretation, just algebraic. But that's the brilliant stuff, because you see that a lot of geometric truth is actually also algebraic truth. And once you have a theorem with regular geometry, sometimes you can prove it generally algebraically, and then this theorem is true for any algebraic sets of vectors, even if they don't have a geometric interpretation. So remind me that next time. I wish to show you now something else which is interesting. So I do wish, as Sammy said, to show you that it also has a geometric interpretation. So one vector is 1, 2, and the other vector was what was it? 5, no,
5, 3.
5, 3. All right. So the summation, the addition is 6, 5. And what does it mean geometrically? Segment 1, 2, 6, 5. Segment 5, 3, 6, 5. You can see the parallelogram that the two vectors, original vectors created, and their addition is the diagonal of that parallelogram. Agreed? מקבילית. So now history and something that I did not show you. Who started using vectors? Do you think? Do you guess? I don't know.
I mean, I don't think it was
Probably
the
the
Greeks.
Greeks.
I don't think so.
No, I don't think
But like
so.
it's basically the same as complex numbers. Like the way they're displayed.
First of all, I'm not sure when did the complex number starts, but I wouldn't say it's exactly the same. But think about it, magnitude and direction. Why do they need magnitude and direction?
So Isaac Newton.
Yeah, right. Correct. So open the book by Sir Isaac Newton.
They should come with him a lot.
Okay. So
Lord, I think.
32, 4. Closer, yes. Okay. Sorry, I'll take 5 minutes of your time, maybe even less. These are Isaac Newton's. You're not seeing what I'm seeing. Oh, yes. These are Isaac Newton's laws. First law, everybody preserves in its state of rest or uniform motion in a right line unless it is compelled to change as said by forces impressed thereon. Second law, the alteration of motion, acceleration, is ever proportional to the motive force impressed. What is that law?
That's
F equals ma. There is a proportion between the force and the acceleration. This proportion is how much food you ate in Passover, the mass. Okay, and it's made in the direction of the right line in which the force is impressed. Third law, it's not my point. The first corollary, it's quite nice. Suppose this is a ball and you have 2 ropes attached to it. One person, Sammy, tags on the rope in this direction and in this force. Tomas tags on the rope in this direction and a force which is that length. Okay, you see a very geometrical drawing because Newton has Euclid to stand upon. Euclid was the main mathematician for so long. So all of what Newton did was much more geometrical than calculus-y. And here it's vectors. And then he asks, so what will happen to the ball? Right? So you tagged on the rope in this way. Tomas tagged on the rope in this way. They are both attached to the same ball that sits here. What will happen to the ball altogether?
moving.
it will move along this diagonal and get here, which means basically that the vector of this force together with the vector of this force is actually equal as if someone took just one rope and tugged in this direction in this length. Okay, so that's from Isaac Newton. And lastly, the thing I love the most. This is the first corollary to the three laws of Newton laws, right? Seems simple enough. What do you think the second corollary looks like?
Very bad at guessing from how you're mentioning it.
3D? 3D, 3D.
This. So lectures have always been this horrible, right? First corollary, homework. Yeah, this is where I lost the book. I didn't follow it too much. But for us, it was just the vectors. I use it for the vectors to show you that it started from physical ideas. And he didn't do it algebraically at all at this point, I think. But we will see in linear algebra the algebraic approach. And like always, I will show you how does it help me geometrically. So thank you very much. See you in calculus.